Yeah, so hello everyone. I'm a postdoc at ICRA Curtin. I used to be at Monash, that's where I did my PhD. And I used to work on theoretical modelling of accreting neutron stars, which is why I was involved in ANITA. But now at Curtin, I do a lot of radio observations. And so they asked me to come here and speak about radio observations of tidal disruption events, which is an interesting choice for a theoretical summer school. But here we are. So just to get a little bit of a gauge, how many of you have ever taken a radio observation with a telescope? Woohoo! Congratulations. Okay, so that's about what I expected. Today I am not going to go through the theory of radio observations because I find it very dry. Radio interferometers are awfully complicated. But the key thing that we need to know for tidal disruption events is that radio observations are very expensive. So even more expensive than optical spectroscopy. So that means if we want to take observations of TDEs, we need to make sure that we're very sure it's a TDE to then go and follow it up. But at the same time, the things that we can learn about TDEs from radio observations is very powerful, in my opinion. All right, so this session is split into two parts. Hopefully it won't go for the whole time. I do have a lot of slides, but we don't have to go through them all, and it's very interactive, so feel free to ask any questions at any point, and I can try to answer them. So the first thing I wanted to do was give you a bit of an overview of the observational properties of TDEs, and a bit of a primer to synchrotron emission, which is the main driving source for radio emission in many astrophysical transients, actually. So we have tidal disruption events. We've heard a lot about them so far, so hopefully you're all fully aware of what a TDE is. But the most interesting thing to me is that essentially, so when Marquis in 1988 first came up with this concept of a tidal disruption event, he said that about half of the stellar debris is bound to the black hole and about the other half is unbound. And so when we think about radio observations, what we're interested in is that unbound debris, because that is the stuff that will be producing the radio emission. And that is about half of the star. So there's a lot to be learned and a lot of stuff there that we can only probe really through radio observations of these events. So in tidal disruption events, we have jets and outflows. There are only two really good candidates for strong relativistic jetted TDEs. But that's not to say that all TDEs don't produce jets. It's just that they are very narrow collimated beams of light, and so you have to be very lucky for them to be oriented towards you. But we, again, don't really have evidence that other TDEs produce jets, so it's a bit of a debate about whether or not TDEs even produce jets. But we do have very good evidence that about half of TDEs produce outflows in some form. Now, that form is hotly debated, so we will go through what the different types of outflows in these events could be. But the key thing is that whether it's a jet or some kind of other shaped outflow, it is driven by synchrotron emission in the radio. So we're going to go through what synchrotron emission actually is, but it's effectively electrons in the outflow interacting with the circumnuclear medium via shocks and producing radio emission. So the key thing is that radio observations trace the ejected material, which is about half of the star. So there's a lot to be probed using radio emission. And in the radio, we tend to see these peaked spectra that evolve over time, over month time scales. And initially we thought that would only be visible for about 1 to 2 years. That is wrong. I have been monitoring a TDE in the radio that's still evolving for 4.5 years now. So they very slow, very long evolving things in the radio. But they really are split into two categories. So we have the jetted relativistic events. This is a light curve of AT 2022 CMC, which was a very exciting event that went off, I would say last year, but it was the year before last now. And again, these are very energetic. They have a non-thermal X-ray spectrum. And this one was at a redshift of 1.1, so extremely distant, and yet we were still able to see emission in the form of a jet from this event. But that being said, we only know of two good candidates of this type of TDE. So when I'm talking about radio emission for TDEs, I'm probably not talking about relativistic jets. So then we have non-relativistic events. This one is my favorite, AT 2019 AZH, also known by ZTF as Jamie Lannister. ZTF like to name their TDEs, it's a really long story. But this one is what we call a non-relativistic TDE in that it didn't show good evidence of a highly collimated energetic jet, but it did show a radio outflow. And I think that radio outflow is consistent with a more spherical shaped structure that is from either an accretion-induced wind or collisions of the debris streams ejecting material. And these show a very thermal X-ray spectrum, so much softer, and they're much, much more common. So Katie yesterday showed us the multi-wavelength properties of TDEs excluding radio, so now you get to see the radio as well. So this is 2 TDEs that have radio, optical, and 2344 also had an infrared flare, which is thought to be a dust echo. But what you can see here is that the optical flare usually happens first and is usually the shortest thing, and the radio starts much later and lasts much longer. So we're talking up to years post the initial optical flare. We see this long-lasting radio flare, and it was the same for VWL. So radio emission rises last and is significantly slower to evolve than at other wavelengths. Yeah?
Maybe a bit technical, but there's this one outlier close to the peak. If you go one, yeah, is that new?
So the long answer is that the radio, these are very compact radio sources. They're very distant, and so they actually suffer from an effect called interstellar scintillation, which is variability not intrinsic to the source, but intrinsic to the wave propagation as it comes through the galaxy to us. And so this can cause fluctuations in the, like random fluctuations in the brightness that we see, up to 100%, depending on how compact the source is and on the bit of the galaxy that it's coming through. So that bit fluctuation there, we could probably put down to just interstellar scintillation because we know it is a very compact emitting radio source. So probably real, but probably not intrinsic variability to the source, probably more to do with our galaxy, unfortunately. Cool, okay. Yeah?
Since you're stopping for a question, so when you were saying we've only seen 1 or 2 possibly jetted ones, is that consistent with the probability of having a jet pointing towards us?
I mean, I guess so. The thing is, what I'm about to say is that we have not actually got very many radio detections of TDEs. So like, probably like 1 to 2% maybe, if you think about the angle of how you've got 360 degrees, the jet's going to be like less than 10 degrees. So maybe, but again, more data required to confirm or deny that. But the thing about relativistic jets is that when they initially are launched, they're very collimated and they're going very fast, but they do decelerate. And when they begin to decelerate, they begin to spread laterally. And so we should actually see that lateral spreading of an off-axis relativistic jet in all events if they all produce relativistic jets. But we don't see that evidence in all events. We have seen good evidence of an off-axis relativistic jet in a couple of events, but again, not all of them. But again, yeah, so there's a bit of debate about whether or not they actually all produce jets or whether only some of them do. Cool, okay. So radio detections of TDEs. This is the total number of radio detections of TDEs we had 5 years ago. So we had only detected 4. And this is a light curve. So time on the x-axis, radio luminosity on the y-axis. You can see Swift J1644, that very bright one at the top in the green crosses. That's a relativistic event. And then we had 3 non-relativistic events. So things were pretty dire. There was not a lot to be said about TDEs in the radio because we did not have much information. But in the last 5 years, we've had some really targeted campaigns with radio telescopes to follow up all TDEs that we can to see if they produce radio emission. And so now the population looks something like this. So now we have more than 20 radio detected TDEs. It's great, however, they all do very different things in the radio. So you can immediately see in this plot, they're not all following the same rise and decay timescales. They're not all the same luminosity. Some of them are rising, some of them decay early and then start to rise again at late times. They're all behaving very, very differently. And so we have to try and explain this with our knowledge of what is producing this emission and how these events should evolve. And so I just want to point out that these are the relativistic TDEs. So you can see there's a real dichotomy in the population. These are extremely luminous, evolve on different timescales, and look quite different to the non-relativistic TDEs, which is all of these ones. But however, some people do claim that some of the non-relativistic TDEs, especially the ones that are rising at late time, that they are off-axis relativistic jets. So it's perhaps not as clear that we have jetted versus non-jetted, but there is definitely a clear difference in these two populations at the moment in the radio. Yeah?
So is there a threshold for determining if a TD is relativistic or not?
Yes, and so the key, I mean, in the radio, you can immediately see it's based on luminosity alone. If it's more than 10 to the 40 ergs per second is probably a relativistic event. But the other thing is the multi-wavelength properties. So the relativistic events in X-rays produce much harder X-rays, so more energetic X-rays, whereas most of the non-relativistic ones don't actually produce X-rays, but the ones that do are very soft, so much lower energy X-rays. And same in optical, there's CMC, the yellow triangles, the relativistic one, that was actually discovered in optical. And it's at a redshift of 1.1. So it was extraordinarily bright in the optical compared to the non-relativistic events. So we look at the multi-wavelength properties, but in the radio, the spectra look quite different and evolve on different, it's all, different. Okay, so what have we learned in the past 5 years about radio emission from TDEs? Well, we've learned that it's relatively common. So we've looked at, I'm part of a VLA large campaign where we've looked at all optically discovered TDEs in the Northern Hemisphere at a redshift less than 0.1, and we found radio emission in about 50% of events, detectable radio emission. So it's pretty common, but not all events do produce detectable radio emission. There's a lot of diversity in the population, and then we have these rising radio TDEs at late times. So these are called late time radio flares, and they were really discovered in the last 3-ish years, I want to say. And this is work mainly led by Yvette Senders and Asaf Horesh. And so you can see we have these events, the ones that I've highlighted in colour here, that are rising very quickly, more than 1,000 days post-stellar disruption. So this is very difficult to explain. But the leading theories are that either the black hole did all of this accretion, swallowed all of this material, and then 1,000 days later it suddenly launched a new jet. Not impossible. And the other theory is it could be an off-axis relativistic jet. So again, as I said, you have this really collimated, highly energetic beam of radiation. At late times, it decelerates, starts spreading laterally, and that's when you start to see the radio emission rising again. I also like to think that some of these could actually be new interactions with the interstellar medium. So if you have a particularly dense clump of gas in the galaxy that the outflow hits, it can re-energize the shock a bit, and you can get a bump in the light curve with some extra energy being produced. But basically, there's a lot of different things happening in the radio, and we need to find a way to explain these in a self-consistent way. So in order to do that, we don't just look at light curves. Ideally, we look at spectra. So these are radio spectra of TDEs over time. So on the x-axis, we have frequency. We're not working in wavelength space anymore. We're working in frequency. And on the y-axis, we have flux density or flux brightness, however you want to think of it. And so you can immediately see that these spectra over time change pretty rapidly and evolve. And so that is key to the mechanism that's driving the radio emission and allows us to place constraints on the physical properties of this outflowing material. So on the right there, we have AZH, my favourite TDE. I think surely everyone has a favourite. Hopefully by the end of this, you'll have a favourite too. And it started at the purple and kind of rose while the peak was shifting down in frequency and then began to fade away. Same with Assassin 14Li. Assassin 14Li is a bit complicated because it actually had a radio source before the TDE happened. And so they had to subtract off this host emission, which is like this constant emission, and then they got some transient evolving emission, but the subtraction is complicated and doesn't always work perfectly. But both of these, you can see they have these peaked spectra in the radio, and the peak evolves to lower frequencies over time. And they change on timescales of months. So the open questions are, what is producing the radio emission in TDEs? And what drives the differences in the radio emission we see from these events? But the other issue is that in the radio, we don't resolve these sources. They're all quite distant and they're very compact objects. And so all that we ever see in the radio is a point source. So this is a lovely point source. This is a radio photo, if you will, of J2344, which is an X-ray discovered TDE. This paper was accepted last week, so please enjoy it. And this is what they look like in the radio when we image them. This is an ATCA image, so the beam is a little bit elongated, which is why it looks slightly oval and not like a perfect circle. But we're not resolving any structure at all. All we're seeing is a single point source. So how can we learn things about the size and the evolution of the outflow if all that we're seeing is a single point source? And the other thing to point out is that we have looked at some TDEs with VLBI, which means you get much higher resolution radio images. But again, they're all too distant. We haven't yet resolved, except for one very close one, which some people claim isn't a TDE. We haven't yet resolved any radio structure from an event because the main issue is that they fade over 3, 4, 5 years. And in that time, they don't grow big enough to be able to resolve them, even with the like a very long baseline interferometry networks that we can use. So what can we learn about these events without resolving them in the radio, but we still want to know what is producing the radio emission, why they all look different, and how we can learn about the outflows that were produced. So this is a really nice graphic from DJ Pasham. This was in the AT 2022 CMC paper. So radio observations probe the ejected material, which can be up to half of the star. So there's a lot of mass in this ejected material. And we can get constraints on the emitting region size, the energy in the emitting region, the velocity of the outflowing material, and we can also get constraints on the ambient density of the surrounding medium. But how do we do that? So we have this basic picture. So this is the case of a jet, where you have the TDE that occurs, you have this stellar debris stream, and you have these shocks from collisions as the debris circularizes. So we have accretion occurring, so we can have outflows driven by accretion-induced winds or jets in the case of this one, or we can have outflows driven by collisions of that stellar debris stream. So in the case of a jet, that jet drives into the circumnuclear medium. The circumnuclear medium in a galaxy is quite dense, we think. In the center of a galaxy, there's a gas and stuff around. And so that jet creates a shock as it hits that gas and stuff in the center of the galaxy and produces emission. Now, jets are very funny because you can actually get radio synchrotron emission from the interaction with both the shock produced by it hitting the circumnuclear medium, but also you can have shocks internal to the jet because it's a very highly energized beam of radiation. You can have electrons kind of shocking each other, and that can also produce synchrotron emission. So there are two main drivers for synchrotron emission. One is internal shocks in the jet. The other is external shocks with the external surrounding medium. And so this is the case of a jet, but in the case of an external shocked outflow, it could even just be a spherical cloud of material moving outwards, and you can have this shocked region all around the edges. But in order to understand, why the spectra look the way they do, why they evolve on the timescales they do, and how to constrain the radio emitting region sizes and things, we need to know a little bit about synchrotron emission. So synchrotron emission is effectively, you have a shock, so you have some cloud of electrons being accelerated, hitting something relatively dense, the cloud of the external medium or each other in the jet, and this produces, so the electrons get accelerated to relativistic speeds, and because the magnetic field compresses, electrons accelerate around the magnetic field, and this produces synchrotron emission. So the electrons can be accelerated into this power law distribution, which is very characteristic of synchrotron emission. So you have electrons going around magnetic field lines producing emission, tends to be seen in the radio. The thing about synchrotron radiation is it actually is this power law, and it, depending on the properties of the source, can peak anywhere outside of radio frequencies as well. But with tidal disruption events, the emission that we see at X-rays and optical and infrared is dominated by other processes. And so we don't really see the synchrotron emission at those higher frequencies, even though there should be some emission from synchrotron radiation at those higher frequencies. So the best place for TDEs to probe the synchrotron emission is at the lower frequencies in the radio. And so that's where we see that. So electrons are accelerated into a power law distribution. If you think you've got individual electrons, each electron is being accelerated into this power law. We get the sum of the individual electrons contributing to the overall spectrum, if we think of flux versus frequency. And it ends up actually just looking like a single power law. Even though you have a whole population of electrons, they're all kind of accelerated at slightly different frequencies and energies and things like that. But in the end, they end up being accelerated into this single power law. So it's the sum of the individual contributions. But the most interesting thing for synchrotron emission is these characteristic break frequencies, so where the peak of the spectrum occurs. And the other thing about synchrotron emission is it's not just TDEs. So synchrotron emission is responsible for many radio emitting sources in astrophysics, including gamma ray burst jets, supernovae outflows, AGN, and tidal disruption events. So when we see this characteristic synchrotron emission, it doesn't necessarily mean that the thing we're looking at is definitely a TDE. It could be any number of things, primarily be AGN. The amount of AGN I have looked at by accident because it looked like a TDE. But AGN can all do very, very weird things. Okay, so in order to constrain things in the radio, we need to know how to model the synchrotron emission. And I guess this is where the theoretical component of this stuff comes in. So the electrons are accelerated into a power law distribution. So the number density of the electrons is proportional to gamma to minus p. Gamma is the Lorentz factor of the electrons. So that's kind of how quickly the electrons' momentum and things like that change, so the Lorentz factor. So after being accelerated into this shock, the electrons will also cool. So this population of electrons will cool because of radiative losses and adiabatic cooling. Now, there are many different regimes that you can be in synchrotron emission. It's all extremely complicated, but I'm going to focus in on the one where we tend to see the tidal disruption event emission. And the key thing that we need to understand is that there are several power law segments that make up a synchrotron spectrum, and they join at these break frequencies. So this is a plot from Greneau and Sari 2002 paper. This was made for gamma ray burst afterglows, but it works extremely well for TDE afterglows as well. And so we have these kind of three important break frequencies. So one is the self-absorption frequency, and that means at this frequency, below the optical depth to synchrotron self-absorption is 1, and above it is higher. And so, I mean, if you think of these emitting electrons, for every emission process, you also have an absorption process. So we have this thing called synchrotron self-absorption. So the source can actually become self-absorbed. So you get a drop-off in emission on the lower side of the frequency spectrum. So that's kind of what causes that slope on the lower frequency side. Then we have a minimum frequency, so the typical frequency of the minimal electron power law. So they don't emit at all frequencies. They kind of drop off at some minimum frequency. And then we also have the cooling frequency, and the cooling frequency is the frequency where the cooling time equals the dynamical time of the system. So again, you'll get a bit of a drop off on the spectrum if it's above or below the cooling time, depending on where the cooling time is. Okay, so we tend to say that...
What are magnetic fields, for instance? Is that, no?
Like 1 to 10 to the minus 2, 10 to the it depends. Not extremely well constrained, but somewhere around.
And you start to be compressed. It's supposed to be, when you're looking down the jet, is it you're looking perpendicular to the fields? Or is that?
So it depends on the system as well. But yeah, Okay, so this is what we expect to see for a TDE in frequency on the x-axis, flux on the y-axis in the radio for a synchrotron self-absorbed source. So we're in the regime where it's the minimum frequencies on the left, the peak of the spectrum is associated with the self-absorption, and the extra break on the higher frequency side is the cooling frequency. So this means that we expect to have a peaked spectrum. The slope, the power law slope on the lower frequency side should be 5/2, and the power law on the higher frequency side should be 1 minus p on 2. But where do these powers come from? We need to kind of think about things in a different, well, not in a different way, but we can actually derive these powers because they're not just made up. They actually come from the properties of the electrons and their properties and the property of the external medium that the shock is propagating through. So, okay, synchrotron and self-absorption, we have, I'm going to use, which whiteboard should I use? This one? Okay. So, we have a spectrum, and this is frequency, and this is flux, and it looks something like this. So this break here corresponds to a frequency known as mu SA, self-absorption frequency. And on this side, this slope should be mu to the 5/2, and this slope should be mu to the 1 minus p on 2. And this p comes from the fact that our electrons are accelerated into a power law. So this is the same p. So it's the slope, it's the power law index. And we call this the synchrotron power law index. Sure. Okay, so we are thinking about a population of electrons. The electrons have an energy electron population, and each electron has the energy E equals gamma mc squared. So this is the mass of the electron, speed of light, and this is that Lorentz factor of each of the individual electrons. Okay, so each of the electrons will, so electrons emit most of their power, so they'll have their kind of peak of their emission near this critical frequency. And this critical frequency has a mathematical equation the critical frequency, mu critical. And so this equals gamma squared E, it's to do with the magnetic field because they're being accelerated around the magnetic field lines, over 2 pi mass of the electron, speed of light. So this is this critical frequency. And so the Lorentz factor of the electrons near this critical frequency is gamma equals the square root of 2 pi mc, and then this is the frequency, the observed frequency, so whatever frequency you want, over E, the square root. Okay, so we have some critical frequency at which the electrons emit most of their power. The Lorentz factor of those electrons is this equation here. Now, the energy of the electrons is this, but we're thinking about an ultra-relativistic population of electrons because these are accelerating at relativistic speeds around magnetic field lines. So whether or not the entire shock is moving at relativistic speeds doesn't matter. It could be a non-relativistic shock, it could be a relativistic jet. The electrons within the shock are moving at relativistic speeds. And so...
Small question. Is the critical frequency depending on the power law index of the distribution of the population?
It does, but not directly in this approximation. But yes, it should. I think there are some things in here that will depend on that. Okay, so we're talking about an ultra-relativistic gas. And so the energy of this gas is not the classic, so the Cp over Cv is not 5/3, which is a non-relativistic gas, it's 4/3, which is a relativistic gas. So instead of E being 3k TE on 2, it's just 3k TE. So this is the energy. Okay, so if we then put this, rearrange this and put the energy of the electrons in, we arrive at the temperature of the electrons being related to the Lorentz factor, the mass, and that's pretty much it. So we have a effective temperature of the relativistic electrons, and we can then sub in, we can then sub in the Lorentz factor for the electrons emitting raised to the power of the critical frequency.
Intermediate equations. It's 3e over k probably.
Sorry, no.
Yeah, this one.
You are correct. Okay. So now we can sub this gamma into here and arrive at a temperature which is, did I reverse something wrong?
The 3 is also
E over 3.
Oh, sorry. Yeah, that goes, yeah, okay. E over 3k. Sure, great. Okay, 2 pi me c mu square rooted over EB times this mc squared over 3k, which is this term. Yeah, that's that term, and then this is the gamma. Okay, and so if we sub in, you know, all the constants and approximate quantities, this in units of Kelvin is approximately 10 to the 6. That's an 8. Times by the frequency, square rooted, and the magnetic field to the minus a half. That's not the gravitational constant, that's Gauss. Okay, so we have a temperature of the electrons. And then at a sufficiently low frequency, the brightness temperature of any synchrotron source will approach the effective electron temperature, and so the source will become opaque. And this is that concept of self-absorption. And so the brightness temperature has this equation. The intensity, spectral intensity with frequency, c squared over this 2k mu squared. And so if we set this brightness temperature equal to the electron temperature, because this electron temperature is approaching the brightness temperature, we end up, and rearrange for the intensity, which we can kind of think of as like flux, I guess. We end up with this 2k TE mu squared over c squared, and then we're going to put the TE in, and so we end up with that this is proportional. So we put that in, we have a mu squared times a mu to the half, so it's proportional to mu to the 5/2. Let me put that lower. Mu to the 5/2, and the magnetic field to the minus a half, but we don't really care about the magnetic field. The most important thing here is that the intensity, so flux, of the synchrotron of self-absorbed part of the spectrum, proportional to mu to the 5/2. So that is what we expect to see for that left-hand side of the peak. So this region here, we expect to see this mu to the 5/2 if we're seeing a synchrotron self-absorbed source. Now this derivation assumes that the emitting region is homogeneous, and in reality a synchrotron source is rarely homogeneous. So in reality this tends to deviate from mu to the 5/2, and it can be mu to the less than 5/2. But that's okay, this is a pretty good first order approximation for what we expect to see for the synchrotron spectrum. So likewise we can derive this spectral index, but I don't think we want to do that now. I think we're looking a bit bored. So yeah, we can go through that if you like, or I can point to some notes that will derive that for you. But basically these numbers, so the power law indices and how the spectra look like, don't come from nowhere. They come from the properties of the electrons in this emitting region of the synchrotron source, and they're kind of very standard expected things. But the other thing is that the observed synchrotron emission depends on the physical system properties, such as the density of the surrounding medium, the velocity of the outflow, the total energy carried by the outflow, and also the fraction of energy deposited in the electrons and the magnetic field. So some fraction of the total energy of the outflow is put into the electrons, some fraction is put into the magnetic field. That fraction depends on the physical system.
This is the general thing we get for synchrotron self-absorption.
Yes.
Necessarily.
Not just for TDEs, this is extremely general. So this applies to any radio emitting synchrotron self-absorbed source. And so we often see synchrotron self-absorption in AGN spectra, in GRB jets, in supernovae outflows, in all sorts of things. So these kind of, characteristic power law shapes come from this process of synchrotron emission, which can happen in many different types of transients, radio transients, and other transients.
And what are the typical gamas that we're talking about here? So very
Like 1, maybe 2, less than 10.
really.
Yeah.
So they're not really.
Well,
They're just 5 of them.
yeah, I guess so. Well, for TDEs, but for DRB jets, I think they're usually much higher.
Electron acceleration in the shock. That's just limited by the electron acceleration in the shock.
Yes.
In this, they don't have time to get much higher than the other field.
I guess so. Yeah, probably. Yep. So TDE shocks tend to be quite slow and not wildly relativistic compared to something like a DRB jet. But the relativistic TDE jets do look a lot more like a DRB jet. Okay, so the real question here is, we have this theoretical expectation of what synchrotron emission should look like. But do our radio observations of TDEs that we have managed to take of these 20 or so TDEs look like evolving synchrotron spectra with these characteristic break frequencies? And if so, what can we then constrain about the system? So to understand that, we need to look at the observations. So this is, again, my favorite TDE, AZH. The left-hand side is a light curve, and the right-hand side are the spectra over 2.5 years. So this is how the spectra evolved and what the slopes looked like. And I mean, light curve we can kind of ignore now, but looking at these spectra, knowing what we know about characteristic break frequencies and the power law slopes, we can then say something about whether or not this looks like synchrotron self-absorption, and if it does, we can constrain the properties of the event, and that's exactly what I did with these fits. So these are synchrotron self-absorption models. We can do this for multiple TDEs over time. So these are another 3 events that I've observed where we have multiple epochs, multiple synchrotron spectra, multiple models to constrain. Okay, so I think this is a good point to download the IPython notebook, and you can tell me if these spectra are consistent with synchrotron emission based on what we know what synchrotron emission looks like. So yeah, this tutorial is very like basic, I want to say. So we're just fitting power laws. Classic radio astronomer. But the idea of the tutorial is it should step you through. Initially, we don't fit any model. We can just fit the data for a power law, and we can say, what does the power law look like? Is it what we expect for synchrotron emission? And then it gets a little bit more complicated when you start to think about other things that might be affecting the radio emission that we see, like the host emission from the galaxy and things like that.